Hello, we are Group 1. Our group is covering biological remediation methods. Biological remediation is the remediation of polluted sites using microbial processes and has been proven to be effective and reliable. Bioremediation as a whole can be split up into subgroups, which can include aerobic, anaerobic, ex situ, and in situ. In this presentation, we will discuss the physical mechanisms of each remediation type, along with the influencing factors, field implementation, applicability, and limitations and cost, along with some case study examples. Starting out, looking at the physical mechanisms involved in these processes, we split each method based on if it is ex situ or in situ. Overall, the mechanism behind bioremediation methods is the process of biodegradation performed by microorganisms. However, as we will see, each method differs in terms of setup and applicability. In addition to describing the physical mechanisms of each method, this section will also provide a brief introduction to each method, including listing out some advantages and disadvantages. The ex situ methods include the bioreactor and the biopile. A bioreactor is a vessel in which raw materials are converted to specific products following a series of biological reactions. Conditions in a bioreactor support the natural processes of microorganisms by mimicking and maintaining their natural environment to provide optimum conditions. There are many different types of bioreactors, and as such there are many different operating modes, which include batch, fed batch, sequencing batch, continuous, and multi-stage. Depending on the type of bioreactor used, the polluted feed can also be entered as a dry matter or as a slurry. Included in this slide is a picture of a typical bioreactor in which contaminated soil is treated through the use of a biocell. Bioreactors can be used to treat soil or water polluted with volatile organic compounds, VOCs, including benzene, toluene, ethylbenzene, and xylenes. The applications of different bioreactors for bioremediation processes have resulted in the removal of a wide range of pollutants as seen in this table. Also, looking at the table, you can see some different examples of bioreactors, such as batch reactors and stir tanks. The advantages of bioreactors include the ability to control parameters. A challenge for all biological remediation methods is keeping the microorganisms alive, meaning that parameters such as pH, agitation, and aeration rates have to be carefully selected. Bioreactors allow for this careful adjusting of parameters and as such can create maximum biological degradation while minimizing abiotic losses. Some disadvantages include the cost of creating and using a bioreactor. Bioreactors are ex situ, meaning that there is a cost associated with physically moving the contaminated material to the constructed reactor. Next, biopiles are an ex situ solid phase biological process for converting contaminants to low toxicity byproducts. Biopiles are aerated with the use of perforated pipes and blowers in order to control the progression of biodegradation more efficiently by controlling the supply of oxygen. In order to conceptualize what a biopile is, it is useful to think of it as a composting pile. However, this comparison is not perfect. In traditional composting piles, they're aerated by tilling and manually turning, whereas biopiles are aerated more aggressively by forcing air through the pile. So it's like a complex composting pile. Here's a good picture of a typical biopile system. You can see that soil is excavated and piled into mounds, where the organisms already living in the soil are used to degrade contaminants. Air is piped through the soil, and nutrients and moisture are added to speed degradation. In this picture, it is a little easier to see all the components of the biopile, which include aeration, irrigation, nutrient and leachate collection systems, and a treatment bed. An advantage of biopiles is that, similar to bioreactors, the conditions such as temperature and airflow can be controlled to ensure that maximum biodegradation is occurring. In addition, biopiles have been proven to be effective at limiting the volatilization of low molecular weight pollutants. A disadvantage is that biopiles can take longer to remediate when compared to slurry phase processes, and that biopiles are a static treatment process, meaning that it may result in less uniform treatment when compared to processes that involve periodic mixing. The in situ methods include permeable reactive barriers, PRBs, and phytoremediation. There are many different types of PRBs, but in general, a PRB is an in situ technique used for remediating groundwater polluted with different types of pollutants, including heavy metals and chlorinated compounds. In this technique, a permanent or semi-permanent reactive barrier, mostly made up of zero-valent iron, is submerged in the trajectory of polluted groundwater. As polluted water flows through the barrier under its natural gradient, pollutants become trapped and undergo a series of reactions resulting in clean water. These reactions can either be precipitation reactions, causing the contaminants to drop out, or redox reactions, causing the contaminants to transform into a less toxic compound. Ideally, the barriers are reactive enough to trap pollutants and permeable enough to allow the flow of water, but not pollutants. PRBs are meant to be passive, with little energy input, inexpensive, readily available, and accessible. The effectiveness of PRBs really depend on their reactive media. As mentioned above, zero-valent iron is a typical reactive media, however, it is not the only option. Looking at this table, clay, organic substrates, microorganisms, and some others can be used as media and are effective at removing a number of pollutants, including nitrites, nitrates, and benzene. An advantage of PRBs is that they have a history of being effective. As of 2007, only 3 PRB failures have been reported which were not caused by design flaws, meaning if designed correctly, a PRB will more than likely perform as intended. However, a disadvantage is that PRBs are relatively new. The first one was only installed in 1991, meaning that long-term data doesn't exist yet, and from the data that has been recorded, there is a suggestion that there is a decreased performance associated with long running times. The last method we are looking at is phytoremediation. Phytoremediation is the direct use of living green plants for in situ removal, degradation, or containment of contaminants in soils, sludges, sediments, surface water, and groundwater. The uptake of contaminants in plants occurs primarily through the root system, in which the principal mechanisms for preventing contaminant toxicity are found. The root system provides a high surface area that absorbs and accumulates the water and nutrients essential for growth, as well as other non-essential contaminants. Seen in the picture below is a cabbage plantation that is growing close to a zinc smelter in Poland. The cabbages are being used to remediate the high concentrations of lead found in the soil as a result of the zinc smelting. Included in this table are some examples of specific plants and what pollutants they can remediate. The plant names are in Latin, so I won't try to pronounce them, but looking at the table, plants can be used to remediate gasoline, diesel, lead, and cadmium, to name a few. A few advantages of phytoremediation include: it is a low-cost, solar energy-driven cleanup technique, it is useful for treating a wide variety of environmental contaminants, and through a process called phytomining, any precious metals that bioaccumulate in the plants can be recovered and have the possibility of being sold, therefore offsetting some of the cost required to set up this method. And lastly, some disadvantages include a long remediation time, and it can be difficult to keep an entire field of plants alive, especially if the pollutants are toxic.
Here, we'll be looking at the influencing factors that take part in biological remediation. Some of the key players in this type of system is bacteria, as without it, your processes will not proceed forward. The most important physical characteristics of note in biological remediation will be soil type and nutrients, temperature, pH, and the concentration of the contaminants will also play an important role. First, let's look at the soil type and the nutrients in it. The nutrients present in the soil is what will stimulate processes and growth for the microorganism. For example, nitrogen and phosphorus are essential for most microbial cell growth. This is also important for anaerobic microorganisms as well, as they use inorganic chemicals such as NO3, SO4, etc. as electron acceptors. Soils will also have different moisture levels, which different microorganisms may require, but systems with too much moisture or saturation may actually inhibit aerobic processes, as it will limit the amount of oxygen received. In looking at soil types, sequestering can also happen. This is where particles of the contaminants may get stuck in pores too small for water to access and will not be influenced or react with the rest of the system. In this case, you may need some sort of chemical that will increase the solubility of the contaminants. Next up, we will look at the temperature's influence. Temperature will influence the rate of enzymic reactions, as the rate tends to increase with temperature until it hits an upper limit. For example, thermophilic bacteria, such as those found in hot springs or deep-sea hydrothermal vents, tend to thrive in temperatures up to 60 degrees Celsius, whereas mesophiles, which is what we will commonly work with, will be happy in their optimum temperature, which is around 25 to 40 degrees Celsius. pH must also be taken into consideration in the system, where we normally want to keep things around a neutral pH of 6 to 8, or in other words, not too basic or acidic. Certain bacteria can only exist in specific conditions, and the pH will also influence the effect of soil nutrients and their availability. What most people seem to overlook is the concentration of contaminants and how that plays a role in the system. If the concentration is too low, the contaminants may remain undegraded or degrade very slowly due to the availability of the microorganisms. In contrast, if the concentration is too high, the contaminants may actually become toxic to the organisms, despite it being biodegradable at lower concentrations. This can also occur when an intermediate builds up, for example, vinyl chloride during TECE biodegradation. And this must be taken into consideration when looking at a system and how one might practice biological remediation.
I'm going to introduce more about influencing factors of aerobic and anaerobic remediations. As we know, aerobic microorganisms metabolize the organic matter in the pollution, and they have inorganic end product. For example, carbon dioxide, ammonium, and water. And here we have 5 main factors will influence aerobic remediation: presence of oxygen, types of contamination, types of soil, chemical oxygen demand, pH, and temperature. For presence of oxygen, we can see here there is a cartoon diagram describing oxidative bioremediation. Bioremediation uses oxygen as electron acceptor. Aerobic technologies may also change the ionic form of metals. If a site contains mixed metal and organic waste, it is necessary to consider whether the oxidized forms of metal species will still harmful to environment. And here is a figure, shows the redox zone's response to a typical plume moving through an aquifer. We are able to see distinct redox zones are built, and there are anaerobic reactions happen right near the spill. While the redox reaction is continuing, aerobic reaction eventually happens. Therefore, in some cases, enhanced aerobic remediation will have additional oxygens added to keep the efficiency. The second one is a type of contamination products in the soil. Aerobic bioremediation is most often used at sites with mid-weight petroleum products, for example like diesel fuel and jet fuel, because lighter products such as gasoline tend to volatilize readily and can be removed more rapidly using other technologies like air sparging or soil vapor extraction. Heavier petroleum products such as lubricating oil generally take longer to biodegrade than the lighter products. Although enhanced aerobic bioremediation technologies may still be effective, it is generally not practical to use enhanced aerobic bioremediation technologies to address free mobile product or petroleum contamination in low permeability soil. In this picture here, we can see sandy gravel, and gravel would be suitable instead of clay because they have lower permeability. And for the third one, we can see the chemical oxygen demand will also play a crucial role. The chemical oxygen demand test measures the oxygen required to oxidize organic matter in water and contamination samples by the action of strong oxidizing agents under acid conditions. As we see here, chemical oxidation demand requires aerobic bioremediation and can be counted as low-stress remediation. In some cases, aerobic treatment plants encourage the contamination concentration to below the certain amount. In the research, I found that it's 30 grams per liter. And the fourth one is the temperature. Normally, microbial activity is slower at low temperature, and biological processes are pH sensitive. Ideal range of pH for degrading bacteria is 6 to 8. Outside of range of 5 to 9, biological activity is less likely to occur. pH levels within a range of 5 to 9 are desirable, and therefore, in some cases, pH smaller than 5 indicates that a buffering agent might be required to sustain high rates of biodegradation. Except from factors we discussed before, types of contaminations and alternate electron acceptor are quite influential factors for anaerobic reactions. In reactions, bacteria will gain and grow as an atom on a contaminant, and it is replaced with hydrogen. Anaerobic metabolism encompasses many processes, include fermentation, methanogenesis, reductive dechlorination, and metal-reducing process. Nitrate, sulfate, carbon dioxide, oxidized metals, or organic compounds such as chlorinated hydrocarbons may replace oxygen as an electron acceptor. Here we can see types of contaminants and alternate electron acceptors are critical in this remediation. And the first factor is the types of contaminant. Anaerobic metabolism are used to degrade highly halogenated contaminants, though some petroleum hydrocarbons may also be biodegraded anaerobically. For example, PCE and TCE we always encounter in our homework assignment, and other type of contaminants may not have such high efficiency. And the second one is the alternate electron acceptor. An alternate electron acceptor, as we discussed before, for microbial respirations in the absence of other metal and ions, elevated levels of ferrous ion indicate that the groundwater environment is suitable for anaerobic dechlorination to occur. And when we applying these influential factors to the ex situ and in situ method, biopile can be considered as aerobic methods. Bioremediation through uses of biopiles involves placing contaminated, excavated soil into piles and stimulating microbial activity through aeration and addition of amendments such as minerals, nutrients, and moistures. Biopiles are typically maintained at soil temperature ranging from 10 to 45 degrees. Moistures from nitrate collection system may be treated and then recycled back to the contaminated soils. Nutrients such as nitrogen and phosphorus are often added to the recycled water. Alkaline or acidic substance may also be added to recycled water to modify to stabilize pH here. And for the ex situ methods here, we can see the biomass increases with time. So there need amount of extra biomass concentration when time passed. And for the bioreactor, microorganisms used for biodegradation in a slurry bioreactors may also grow in suspension in the fluid or be attached to a solid growth support medium. Therefore, the support matrix is critical. Activated carbon can be absorbed as contaminants and slowly release them to the microorganism for degradation. Residence time in the bioreactors varies with the matrix. And for the phytoremediation, it may need environmental factors for plants to live. And we discussed before, probably the plants may not stand for a long time under the toxic environment. And for the permeable reactive barrier, the least reactive constituent will be the most major factor, because at sites where the groundwater contamination includes a mixture of chlorinated hydrocarbons, the design of the PRB usually is determined by the least reactive constituent. PRBs are designed to provide adequate residence time in the treatment zone for the degradation of all toxic contaminations. And here there are very much comprehensive hydraulic factors affecting PRB, and we can see a table of site characteristics and the solution. And we can see here ideal PRB varies along with characterizations.
In this section, we will be discussing the field implementation of the four major bioremediation methods presented in Section 1. The first method of bioremediation presented are bioreactors. Bioreactors are an ex situ treatment method that can be used for aerobic and anaerobic processes. Bioreactors are any vessel designed to support biologically active environment for microbial processes. These can range from crude line depressions in the ground to manufactured metal containers with monitoring equipment. Bioreactors are often made out of stainless steel and are cylindrical in shape. Specifications can vary based on the specific process being targeted for the treatment or the treatment volume. Common bioreactor components include an agitator to mix contents into a homogeneous reactive media, a sparger in aerobic processes to supply oxygen, and a heat exchanger or baffles to maintain a target temperature in the reactive media. Below is a diagram of a laboratory bioreactor with general components listed. Biopiles are the second method of biological remediation listed. Biopiles are an ex situ remediation method that entails excavating contaminated soils and mixing them with a remediation compound. This mixture is stacked into piles and covered to promote degradation. Soil piles can be up to 20 feet high and are covered to prevent runoff, evaporation, and volatilization of compounds. If there are VOCs present in the soil, air leaving the biopile must be treated to prevent VOC release into the atmosphere. After treatment, excavated materials can usually be safely returned to the excavation site. Some drawbacks of biopiles are that they are not usually effective at reducing contaminant concentrations by more than 95%, and are not usually effective for chlorinated compounds. Common components of a biopile system are a treatment bed, an aeration system, irrigation system, and a leachate collection system buried underneath. PRBs and PRTZs are permeable reactive barriers that function as an in situ passive treatment method. These reactive barriers contain biological agents that are placed underground in the path of moving contaminant plume in order to treat the moving groundwater as it passes through. Usually these are selectively permeable to certain compounds. Contaminant removal methods include sorption, precipitation, chemical reaction, and other biological mechanisms. PRBs are installed by digging a long trench in the path of contaminated groundwater flow to place the treatment barrier. The final in situ treatment method implemented in the field is phytoremediation. Phytoremediation is the use of plants and their associated microorganisms to concentrate or degrade contaminants from groundwater. Contaminant concentrations, depth within the rhizosphere, and bioavailability all play roles in the ability for phytoremediation to intercept, absorb, and accumulate contaminants. In addition to the provided examples in Section 1, some additional common plant species used for phytoremediation are Indian mustard, which is useful for accumulating heavy metals, willow, which accumulates heavy metals and hydrocarbon fuel components, poplar, which is effective for treating large volumes of chlorinated solvents, and Indian grass for the remediation of various herbicides, pesticides, and petroleum hydrocarbons.
The first case study in this section is from the creosote remediation project in St. Louis Park, Minnesota. Creosote is a dark brown oil distilled from coal tar and is used as a wood preservative and contains a number of phenols and other volatile organic compounds. From 1917 until 1972, Riley Industries operated Republic Creosoting Company, a coal tar distillation and a creosote wood preserving plant on an 80-acre site in St. Louis Park. From 1917 until 1939, waste containing coal tar and its distillation byproducts were discharged directly into a ditch that ran the length of the site. These wastes then flowed into a peat bog on the southern portion of the site. An oil-water separator was installed in 1940, but the Republic Creosoting Company continued to discharge contaminated waste into the peat bog for the duration of the company's operations at the site. As shown in the diagram, the prolonged discharge led to widespread contamination of both water sources and soil sources in the surrounding area. Historical records suggest that there were more than a dozen wells on the site, with depths varying from 50 to more than 900 feet. Over time, creosote and waste materials likely seeped down several of these wells, either directly from the surface or via multi-aquifer transfer, and contaminated the groundwater. The soil elsewhere on the site also became contaminated from coal tar and creosote that dripped from leaky pipes, various processes, materials that spilled during transport, and creosote wood preserving chemicals that washed off freshly treated lumber. In 1978, the state of Minnesota shut down several public drinking water wells in the vicinity of the site. The city instituted a water conservation program due to daily shortages of clean drinkable water. In 1979, 28 multi-aquifer wells were either reconstructed or abandoned to prevent the spread of contamination in groundwater. By this time, many community residents had become extremely concerned with the quality of water. After much public pressure and the prolonged ongoing lawsuit between the EPA and the Minnesota Pollution Control Agency, or MPCA, versus Riley Industries, the EPA provided funds to the MPCA to clean out the contaminated wells. The site was listed on the National Priorities List in 1983. In 1984, a record of decision was issued requiring Riley Industries, the potential responsible party, to build a treatment plant for the existing contaminated municipal wells and assist with containing the contaminant plume from reaching other wells by building a source control system in the upper aquifers. Riley Industries eventually came forward with a practical, cost-effective remediation plan that expedited the cleanup and reuse process. Under the settlement, the city agreed to share the responsibility of operating and maintaining the municipal water treatment plants and performing long-term groundwater monitoring. Thus began the construction. In addition, the Riley plant was demolished in 1972 and the site was leveled. Evidence suggests the city brought in topsoil in order to establish grass, and the Riley site was used as a park as soon as the creosote plant was gone. This early topsoil cover and subsequent soil cover brought in more recently was tapered to meet the grade established by a lined stormwater pond by Louisiana Avenue North and Walker Street and by other paved areas at the site. Based on observations, the soil cover is not less than 6 inches and is more typically 1 to 2 feet thick throughout the Riley site, with the exception of the athletic fields. As shown in the slide points, the water and soil remediation plan had a large impact on the local environment and surrounding areas. The treatment plant operations resulted in improved water quality to a high extent. Large amounts of the VOCs were treated out of the water. The cases of cancers and long-term and short-term waterborne diseases dropped in the surrounding population. Over the years, the remediation and strict monitoring by the authorities improved drinking water standards in the area. In addition to this, the soil remediation enabled site redevelopment years down the line. The efforts resulted in the construction of various infrastructure in the area. As an example of site redevelopment, apartment and business complexes were built together on the site. In 2002, the city built a recreational park to complement the residential housing in the north and south ends of the site. The site is now a place where community members can gather to enjoy the amenities the city has worked so hard to create. Currently, the site is populated with condos, townhouses, and other recreational infrastructure and spaces. In addition to this, as a requirement of law, any work that involves digging in contaminated areas of the Riley site must first be approved by the MPCA and EPA. Work plans must include safe handling of any waste or contaminated soil that is found, in addition to air monitoring to protect workers and nearby residents if waste or contaminated soil is encountered.
In case study 2, we have presented on the slides how a town in California was invaded by a toxic plume. The plume stretches about 1.5 miles long by a 1/2 mile wide and is located in Moffett, California. In the picture shows the 2 main hotspots, which the study indicates as the major contributors to the overall diverging field zone of the TCE toxic plume. The toxic solvent leaked from underground tanks and spilled all over the area you see in the image. You wonder how this case study came about. Bay Area's investigative unit first dug into this toxic plume and its implications for residents' health in the year 2012. The investigative unit's initial probe then prompted California's Cancer Registry to open its own investigation. After several months, the Cancer Registry found a higher than expected incidence of certain cancers among residents living during certain time periods in the area. The EPA has been monitoring and extracting toxic trichloroethyl, or TCE, from groundwater and soil in and around Moffett Field. TCE was used as a cleaning solvent and was once commonly used by the military as a budding semiconductor 30 years ago. Several years after its common use, experts discovered TCE was, in fact, a toxic solvent that causes cancer in people and heart deformities in unborn babies. The EPA stated that they did clean up the site when it occurred, however, then admitted that they've missed what they're now calling hotspots, located along one of the streets. After discovering the lingering toxic plume, EPA officials began putting ventilation systems in homes and office buildings. After all said and done, it was discovered by California State Registry that analysis of the 3 decades of health data found a higher than expected number of people living amongst the area and surrounding areas who contracted a group of cancers the registry scientists call non-Hodgkin's lymphoma. The higher than expected incidence of these cancers occurred during the years 1996 to 2005.
Today I'm going to talk about the aerobic and anaerobic applications of bioremediation. Aerobic remediation involves microbes that are reacting that requires oxygen to go forward. The bacteria use the carbon substrates as electron donation and the oxygen as an electron acceptor. Usually the applications are for suitable climate environments detailing temperature, the soil characteristics, which are the heterogeneity of the soil, as well as the pH of the soil. And also this includes adequate water and nutrient levels. In general, bioremediation employs accelerated biodegradation of chlorinated solvents and facilitates source reduction and improves the overall effectiveness of the natural attentiveness of the protective remediative. Bioremediation has been very successful in treating soil, sludges, groundwater contaminants with petroleum, hydrocarbons, solvents, pesticides, wood preservatives, and other organic chemicals. Bench and pilot scale studies have demonstrated the effectiveness of anaerobic microbes degradation and the nitrotoluenes in the soils, contaminating and municipal water waste it employs, where the protection and the restoration of the beneficial use of the groundwater and drinking water is not employed primarily for the remediation objective in the facilities where chemicals and or physical, such as pumps and treatment plants, are not technically physically feasible. Facilities with strong evidence in natural attentiveness are good candidates for biological remediation. Biological remediation is also considered facilities undergoing groundwater pumps and treatment remediation by accelerating the rate of remediation with the in situ effective dehalogenation or replacement of the pump or treatment when the contamination concentration reaches an asymptotic level that exceeds the remedial goals. Biological remediation is especially effective for remediating low levels of remedial contaminant concentrations in conjunct with the source removal. Biological remediation is also effective for low levels of residual contamination in conjunction with the source. The contamination groups most often are PAHs, or are non-halogenated SO boxes, and also BTECs. The types of Superfund sites mostly treated for biological remediation have been contaminated through processes or waste associated with wood preservation or petroleum refining. And wood preservation commonly employs creosolvents, and which has high concentrations of PAHs and other halogenated SO-voxes. Similarly, petroleum refining and the reuses of processes infrequently involve BTEX. And the two contaminant groups most commonly treat using the biological remediation are S-voxes and the other non-halogenated X-voxes. It may be difficult to treat them using technologies that rely on volatility, such as SVE. In addition to this, for biological mediation, the treatments often does not require heating, which is good for conserving power. It usually requires relatively inexpensive inputs, such as nutrients, and usually does not generate residual requirements for treatment or disposal. Also, on top of this, for in situ, it does not require excavation of the contaminated site. Compared to other technologies such as thermal desorption or incineration, which usually require excavation and heating, the thermal enhanced recovery, chemical treatment, and also in situ soil flushing, which may also require further flushing of the water. Biological remediation is a cost-effective treatment of non-halogenated S-voxes. Biological remediation, in addition to this, cannot degrade inorganic contaminants. Biological remediation is used to change the valent state of the inorganics and cause adsorption, immobilization of the soil particulates, and precipitation, uptake, and accumulation of the concentration of organics in micro or macro scale organisms. These technologies, while they're still largely experimental, are considered to show promise in the area of biological remediation. Overall, for anaerobic remediation, they're usually only used in aqueous phases, whereas anaerobic are used in non-aqueous and aqueous phases. With anaerobic remediation, it involves the microbes reacting, causing an absence of oxygen, and encompassing many processes, including fermentation, methogenesis, reduction of dechlorination, and the sulfate and nitrate reduction conditions. Depending on the site contamination, a subset of these activities may be cultivated. And anaerobic metabolism, sulfate, nitrate, carbon dioxide, oxidized materials, and organic compounds may replace oxygen as an electron acceptor. This also can be used in intermediate transformation products that may be toxic.
Pictured here is an image showing all of the different types of biological remediation methods. As it was mentioned before, these methods can be broken up in situ and ex situ. Just to recap, we can see that the methods of biological remediation in ex situ include biopile, windrow, bioreactor, and land farming. The methods of biological remediation for in situ include natural attenuation, enhanced methods, and a permeable reactive barrier. The enhanced methods include biosplurging, bioventing, biosparging, and phytoremediation. Now that we have recapped these methods, we can now discuss some of the limitations of these methods, both in ex situ and in situ. For limitations in ex situ, it is extremely difficult to control the volatile organic compounds, or VOCs. Excavation cost would also be a limitation in ex situ methods. In land farming, a big limitation is the large operating space. On the other hand, the biopile process is able to conserve space compared to land farming. However, this means a lack of power supply at sites, more complicated engineering techniques, and high maintenance and operation cost. Another limitation is excessive heating of air. This leads to soil drying, which can result in inhibition of microbial activities and promote volatilization rather than biodegradation. In situ bioremediation techniques generally do not require any excavation, which means little to no disturbance in soil structure, as well as more cost efficient compared to ex situ methods. However, in situ has its own limitations. For limitations in situ, it is extremely hard to predict the direction of airflow when using processes like biosparging. Another limitation in situ methods has to do with processes proceeding without any form of enhancement. These methods include bioventing, biosparging, and phytoremediation. Longer remediation time, pollutant concentration, toxicity and bioavailability to plant, depth of plant roots, and plant slow growth rate are all limitations that apply to the process of phytoremediation. In general, the biological remediation method has overall limitations compared to the other 5 methods we have discussed in this course. The most important limitation is the treatment time of biological remediation methods, because this method is more time-consuming than any other method. Another overall limitation is that effectively treated contaminants are limited to compounds that are biodegradable.
For general limitations, there are several additional factors. This is including energy sources, where one primary variable affecting the activity of the bacteria is the availability and the ability of reducing the organic material to serve energy sources. Whether a contaminant may serve an effective energy source for an anaerobic heterophytic organism is a function of the average oxidation state of the carbon in the material. Another limitation factor is the bioactivity and the biochemistry. In terms for bioactivity, it's usually to indicate the microbiological processes. Improving bioactivity implies that the system's conditions are adjusted to optimize the biodegradation. For example, if you're using a biological remediation, it requires meeting a certain minimum rate for adjusting the conditions to improve the biological degradation activities, becoming important in the biological remediation in general to control the advantages. On top of this, contaminant concentrations are very important for influencing the bioactivity and the microbial activity as well. When the concentrations are too high, the contaminants may have toxic effects on the present bacteria, and contrast to low contaminant concentration, it may prevent inducing microbial and bacterial degradations to the enzymes. In addition to this, we also have another factor dealing with contaminant bioavailability. This is different from bioactivity. Bioavailability depends on the grade to which they absorb to solids or are subsequent by the molecules in the contaminant media, or are usually diffused in macro pores of the soil and the sediment. And other factors such as whether the contaminants are present in non-aqueous phase, such as DNAPL or NAPL. Another factor dealing with this is site characteristics. This is usually very impacted on the effectiveness of the biological remediation strategy. Site environment conditions are important to consider for biological remediation, such as the pH, temperature, water content, nutrient availability, and the redox potential. Now I will go into detail about these site characteristics. The pH affects the solubility and the biological availability of the nutrients and the metals and other substituents for the optimal biological growth. pH remains within the tolerance range for a target microorganism. Biological remediation processes prefer pHs that are between 6 and 8. Redox potential, which is another site characteristic, and the oxygen content are usually oxidizing or reducing conditions. Redox potential influenced by the presence of the electron acceptors such as nitrogen, manganese oxides, iron oxides, and sulfates. Another characteristic is the nutrients. Nutrients help the microbe cell growth and division in their regular life cycles. Suitable amounts of trace nutrients for microbe are usually present, but nutrients can be added via inorganic substrates, which usually involve an electron donation to stimulate the biological remediation. Now, for temperature, it usually directly affects the metabolism of the microorganism and consequently the microbial activity in the environment. The biological remediation degradation rate to an extent raises with the increase of temperature and slows with the decreasing amount of temperature. So this is very important overall to maintain temperature control when you're having your biological remediation.
For cost and availability, we'll be looking at normalized costs for the four methods mentioned in this presentation. Normalized cost means the cost per unit mass or unit volume. In particular, the cost will be presented in dollars per cubic foot of water treated. First, we'll look at the cost of bioreactors. This table from GW Technology shows 4 scenarios and the various costs for treating groundwater in each scenario. The total cost consists of the cost of the extraction well, the bioreactor, and the design. As shown in the table, large-scale operations had a lower normalized cost than small-scale operations, despite having a higher cost outright. Costs were also lower for operations under easy conditions, such as low initial concentration of pollutants or simply pollutants that are easy to treat. As expected, costs were higher for operations under difficult conditions, such as high initial concentration of pollutants or pollutants that are more difficult to treat. Costs in the table were given in dollars per gallon of wastewater, so when converted to dollars per cubic foot, we get a low estimate of $157 per cubic foot of wastewater for a large-scale operation under easy conditions, and a high estimate of $1,250 per cubic foot of wastewater for a small-scale operation under difficult conditions. Costs for biopiles were presented in $2,004 and given per ton of soil. Adjusted for inflation, we have a low estimate of $40 per ton of soil for soil contaminated with light petroleum. Soil contaminated with heavy petroleum takes longer to treat in a biopile and is therefore more expensive to treat. This gives a high estimate of $120 per ton of soil. In the next slide, we'll attempt to convert these values to dollars per cubic foot of water. For a large-scale operation, the soil treated in a biopile would have to contain 0.25 cubic feet of water per ton in order to be similarly priced to a bioreactor. This corresponds to a porosity of 0.02, assuming the soil is saturated, which is very low, but if the soil isn't saturated, the effective porosity could realistically be near this value for several soil types. If the porosity or effective porosity of the soil being treated is lower than this value of 0.02, then the bioreactor is the more viable and cost-effective option. If the porosity or effective porosity is higher than 0.02, then the biopile is more cost-effective. For a small-scale operation, the comparison is similar, and it's found that the soil would have to contain 0.1 cubic feet of wastewater per ton of soil for a biopile at this site to be priced similarly to a bioreactor. This corresponds to a soil porosity of 0.008, even lower than the 0.02 estimate for large-scale operations. So again, assuming saturation, this porosity is very low and unrealistic for most soil types. But if the soil is unsaturated, this water content is realistic. If the porosity is less than this value of 0.008, then the bioreactor is once again the more viable option. If the porosity is higher than 0.008, the biopile is the more cost-effective option. For operations of either size, if the soil being treated is saturated, then the biopile will almost always be the better option. Several cases of permeable reactive barriers were given. An average operation seemed to be at the Naval Weapons Industrial Reserve Plant in Dallas. The total cost for the project was estimated at just over $1 million. This was just the capital investment and didn't include maintenance costs, which were said to be significantly lower than the capital investment and therefore negligible. The site in Dallas treated about 1.65 million cubic feet of groundwater per year, and the expected lifetime of the project was 20 years. This accounts for a total volume of 33 million cubic feet of groundwater treated. This corresponds to a very low normalized cost of 3 cents per cubic foot of groundwater. Similar to bioreactors, the cost of phytoremediation operations varies based on the scale of the operation and the conditions of the soil in the site. For a large-scale operation with easy conditions, the cost is $4 per cubic foot of water treated. For a small-scale operation with difficult conditions, the cost is $66 per cubic foot of water treated. Normalized costs for large-scale operations with difficult conditions or small-scale operations with easy conditions will fall between these two values. It's evident that in situ treatment methods cost significantly less per cubic foot of water treated than ex situ methods. Out of all the methods, the cheapest was permeable reactive barriers, or PRBs, with a very low normalized cost of 3 cents per foot.